Okay, so arc length is something that we've actually seen twice. So we saw arc length back in Calculus 1, and then we saw arc length for parametrically defined um, functions in Calculus 2. Okay, so now we're going to learn about arc length for space. In other words, arc length when you have 3D, uh, in 3D, you have space curves and vector functions. And we'll introduce a new concept which is called curvature. Now, curvature talks about, I mean, it's very similar to how it sounds. It gives you an idea of how fast your curve is changing. So, curvature involves derivatives, of course, and arc length also involves derivatives. Okay. So, yeah, so we kind of just as a reminder that this would have been back in Math 3B, right? You define the length of a plane curve. Remember, plane is going to be two-dimensional curve with parametric equations as the limit of the lengths of inscribed polygons. Okay, and our formula was the integral from a to b of the derivative of x plus the derivative of x squared plus the derivative of y squared, square root of that, right? And the idea behind that was a bunch of you're forming a bunch of triangles, right triangles, and this was the change in x, this was the change in y. So the length of the leg was a change in x, the length of the leg was a change in y. And so this was the change in the x prime squared plus the y prime squared was the change in the hypotenuse. And so, of course, I wrote my triangle incorrectly. So it should be like this is the hypotenuse. So that would be your right angle. Okay? So the length of a space curve is defined in exactly the same way. It's just now our distance, right? Instead of distance being the square root of x squared plus y squared, that's for 2D. In 3D, our distance is the square root of x squared plus y squared plus z squared. Okay? So we have our formula, right? So this is corresponds to our x component, our y, and our z, right? And if we make the assumption that all the derivatives of those component functions are continuous, then the arc length is going to be the x prime squared, right? So x prime squared plus y prime squared plus z prime squared, square root that, integrate from a to b. Okay. And another way to write this is to write the magnitude of your derivative vector, because remember, if r is f, g, and h, then r prime is going to be f prime, g prime, h prime, right? So the derivative of, or the magnitude of r prime is going to be the square root of f prime squared plus g prime squared plus h prime squared, right? So if we're integrating that from a to b, that gives us our arc length. Okay, and so that's what we're describing right here. Okay, and it works for both plane curves, which is 2D, and space curves, 3D. Okay, all right. So let's do this example. Find the length of the arc of the circular helix. There we go again with the helix. So we've got a circular helix because if we look at the x and the y components, notice if this is x and this is y, then x squared plus y squared is equal to cosine squared plus sine squared, 1. So this would be unit circle, but the unit circle is now, right, It's traveling in space. Okay, so we want the length of the arc from the point 100 to the point 102 pi. All right, so we know the formula that we need to use. Our formula is going to be length is equal to the integral from a to b square root of f prime of t squared plus g prime of t squared plus h prime of t squared dt. And we've got to figure out f of t, g of t, h of t. We also need to figure out a and b. Okay, f of t is just going to be cosine, so this is going to be f of t. G of t is going to be sine of t. And h of t is just going to be t. Okay, so we'll put cosine of t, sine of t, t. Now to determine a and b, we've got to figure out for what value is of t is r of t equal to 100. Okay, so if r of t equals 100, what is t? And then that'll give us a, right? So a is where the curve starts, right? And then to figure out b, we're going to figure out for what value of t we have the position vector 102 pi. Okay, so let's figure out this. So we need to, in order to solve for t, we're going to solve essentially a system of equations, nonlinear equations, right? So if you're taking linear algebra, that's about solving linear systems of equations. This is not going to be linear. We've got cosine of t equal to 1. Sine of t needs to equal 0. And t needs to equal 0. I love it when this happens because it's very easy to solve. T is equal to 0. And now similarly, if r of t equals 102 pi, then t is equal to 2 pi. Okay, so a is 0 and b is 2 pi. So now for our formula, we said a is 0 and b is 2 pi. So we'll put 0, 2 pi. Now we need f prime of t, g prime of t, and h prime of t. So now if f of t is equal to cosine of t, that means f prime of t is equal to negative sine t. G of t is sine of t, so g prime of t is going to be cosine of t. And h of t is equal to t, so h prime of t is equal to 1. All right, so we're going to put in here, just replace the functions here. So we need negative sine of t, cosine of t, and 1. Okay, so now, of course, 1 squared, that's just 1. Cosine squared, that's just cosine squared. And negative sine t squared is just going to be sine squared. Now, sine squared t plus cosine squared t equals 1 for all values of t, so we can replace that with 1. And 1 plus square root of 1 plus 1 equals 2. This is becoming embarrassingly easy. So now what we have is the square root of 2 dt. We can just bring that constant out, right? Because that's a constant. So bring it out. We've got the square root of 2 times the integral from 0 to 2 pi of dt. But that's just going to be square root of 2 times. So that's like you have a 1 there. So you'll have t and evaluate it from 0 to 2 pi. So that'll just be 2 pi times square root of 2. So 2 root 2 pi. So that is the length of that part of the helix. There we go. 2 root 2 pi.